Chapter 1.3, Problem-Solving Procedures. So in this chapter, we're going to go over a particular problem-solving procedure, a way to solve a problem, and then we're just going to go over some general techniques for solving various types of problems. Now, this chapter kind of requires you to know a little bit coming in, so a little bit about percents, a little bit about algebra, etc., but don't worry too much. I will explain as much as we need to know. So, the main point is, first we're going to learn about Polya's procedure. So George Polya was a mathematician who was educated in Europe and taught at Stanford, who developed a general procedure for solving problems. Step 1 is understanding the problem. 2, devise a plan to solve the problem. 3, carry out the plan. And 4, check the results. So, I'm going to go a little bit more in depth into this procedure. First, understanding the problem. How do we truly understand a problem? We should always start with this. We, of course, would want to read the problem carefully. And we want to read it more than once so that we can make sure that we are internalizing everything that the problem is asking. Trying to make some sort of sketch of the problem and labeling that sketch can be very helpful in directing us towards what we need to do, especially in a geometric type problem. We can make a list of given facts that are pertinent to the problem. Quite often, if it's a word problem, I advise underlining key terms and rewriting information that, like any numerical information that you're given, to make sure that you use everything that is part of the problem. And then finally, determine if you actually have enough information to solve the problem so that you don't waste your time, right? Because not every problem is solvable in life, though most math problems you'll be given on a test should be. Now, next is we devise a plan to solve the problem. So this is only the planning stage. Don't just go straight into it, but take some time to think about what options do we have, and there may be more than one. So ask these questions of yourself. Can you relate this problem to a previous problem that you've worked on before? It's not going to be exactly like a previous problem, most likely, but it will probably relate to something you've done in the past, at least if it's something in this class. Can you express the problem in terms of an algebraic equation? Can we translate the problem into algebra easily? Do we see any patterns or relationships between different parts of the problem, different numbers that are given? Can we express the problem more simply? Now, this is a big one. A lot of word problems involve a lot of words. If we get rid of all of the main words and just extract the key terms and the numbers, it might be a lot easier to parse through what needs to be done. Can you substitute smaller, simpler numbers to make the problems more understandable? So if your problem is working with, numbers up in the millions and billions, maybe just put in what if we just put the number 2 somewhere to make things a little bit nicer, just to see if that'll help us sort of work through it before we have to work with big numbers. But we can even do this with a little bit of estimating as well. So if our number is 287, then what if we just put 300 in there so we can estimate in our head to make an educated guess at the solution? And would a table help? So with all the information we're given, perhaps having a table can also help if you're given a lot of numerical information. So the biggest things to take away from here when planning is, I think, making that educated guess, though. So substituting in easier numbers to work with, and then doing a little bit of quick algebra to make that guess so we can work backwards once we have that, so we can check our answers. That's what we want to do. We want to utilize our educated guess to check our work later. So did the answer we got match with our guess, and does it make sense for the problem? So doing that first so that we are not biased towards our final answer is a really good step to take to help you know when you're getting the right answer. Okay, step 3 is, of course, going to be to actually carry out whatever plan we made. So we use the plan that we figured out in step 2 and we go through and we solve the problem. And then step 4 is very important. It's the step that everybody loves to skip. Checking your answer. Always, 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 but especially in word problems, ask yourself, does the answer you got make sense? Is it reasonable? If the answer is not reasonable, recheck your method for solving the problem and check your calculations. So when that happens, how do we know if an answer is reasonable? In a word problem, it should be pretty easy. If, for example, I asked you, some question about how many gallons of water do we have, and you tell me -2, does that make any sense? No, of course it doesn't. How can you have a negative gallon of water? Or if I ask you for, the area of a classroom, and you tell me it's, 5,000 feet by 5,000 square feet, well, that's not a crazy number, maybe. It's a pretty big classroom, but it's fairly reasonable. It's 50 feet. It could be 50 feet by 100 feet. It's a very big. It's a decently big classroom, but it's not insane. But if you said 5 billion square feet, well, that's one that you'd want to definitely go back and check your work, right? That's not going to be the size of a classroom. But even the 5,000 might be a little bit large. So you might want to think, well, let's just make sure that what we did makes sense, right? So if I had estimated earlier, well, what's a normal classroom size? Okay, it might be normally if it's like 20 by 30, maybe it's this many square feet, etc. Like, I can use that to sort of, especially if I've simplified my numbers, I can say approximately what size it should be. And then I use that. I use my approximation to check my answer. Does my answer match with that? If we are working with, money, and you tell me that you put away $100 a year into a savings account, and then after 10 years you have, you're, a trillionaire, think you would know that that's not going to be right? Think about that. So, one way to check your answer once you sort of realize it's not reasonable, especially, is can you put it back into the original statement? Can you plug it into your algebra equation and actually see that it was equal? That way you can check whether your calculations were correct. Can we use those results for further problems? So, for example, if it's a multi-step problem and we get one answer in one step that's wrong, it's going to make other steps not make as much sense, perhaps, right? So we want to think about that. Is there another way to solve the problem? If you solve the problem in 2 different ways and get 2 different answers, that means something must have gone wrong at some point. Think about all of that. Checking your work is important because you want to get the right answer, right? But also because if I see that you checked your work, well, you're going to get probably more partial credit, even if somehow you did some calculation error in the checking step and so end up still getting it wrong. If I see that you're checking, that means something. But more likely, if you're checking, you'll see when you get something wrong, and so that you can fix it, and so it won't matter anyway because you'll have the answer right. So let's just go over a few select problems in various sort of areas that use a bit of algebra, but we're going to use some problem-solving techniques. So this is like the most algebra most like clearly algebra stuff you're going to see in this class, actually, because it's not a very algebra-based course. So here we have an example on shuttle revenue. So Airport Express shuttle provides service from San Antonio International Airport to downtown hotels, which are approximately 10 miles away. One particular shuttle makes 16 round trips per day, carrying 5 passengers per trip. The fare each way is $18. How much money is received in 1 day of operation for this particular shuttle? So, to begin sort of analyzing the problem, step 1, we want to understand it, right? So we would reread it. I'm not going to reread it out loud, but we would reread it. As I said, I think it's a very good idea to go through and sort of underline key information. So that's what I'm going to do. So some key information would be 10 miles away, 5 passengers per trip, each way is $18, 16 round trips. All of that is important information. And then our goal, we want to think about our goal. What are we receiving in 1 day? In 1 day, right? That's important as well. So, we're going to take all that information, we're going to answer the question, what do we know? I'm going to list all of the information that I had underlined out like this. So the distance from the airport to downtown hotels is approximately 10 miles. Number of round trips per day is 16. Number of passengers per trip, 5. Fare each way, 18. Right? I've got all the information with the numbers just pulled out because that's the only stuff that's really going to be relevant. And so that's what we know. And the second question I'm going to ask is, what do we need? What do we know? What do we need? That's a really good way to guide yourself in coming up with a plan for how to tackle the problem. Write down, what do we know? What do we need? We need the total fare received in 1 day. So to solve, we want to think out, how do I get total fare? How do I find that? Well, we know the fare each way, so we can figure out the fare in both directions, right? So round trips, how much is that? A round trip is going to be 2 each ways. So 2 times 18 is 36. So that's the cost of a round trip. Then the total fare is going to be the number of round trips times how many people are making that trip, because how many people are going to be paying, and then times that cost per trip. So, in other words, something like this. Number of round trips times number of passengers times cost per round trip, that would equal the total received. So writing out what you need verbally, yes, this is actually an algebra equation. I could call it A times B times C, but why not just write out the words here? A would be the number of round trips. B would be the number of passengers, and so on. So I'm just going to leave it as verbally what it is, and then I will directly replace these words with what with the number that represents them. So the number of round trips is 16. The number of passengers is 5. The cost per round trip is, as we've shown, $36. So, altogether, 16 times 5 times 36 is $2,880. Now make sure, last note is, pay attention to that unit. You want to make sure you get your correct units. One way to think about that is, well, we had $36 as part of the problem. There's a little bit of unit analysis that can go into here, but we're not going to talk too heavily about that. Just think about what the question is asking for. It's asking for a price, so you better have a price in the end, a dollar amount. Does this make sense for a dollar amount? Yes, this does make sense. All right, let's try another example. So this one's about saving for retirement. So it's never too early to start planning for retirement. The U.S. Census Bureau data indicates that that at age 65, the average woman will live another 21 years and the average man will live another 19 years. It also indicates that about 33% of the average person's retirement income will come from Social Security. So when discussing retirement planning, many investment firms and financial planners use the graph in the figure, which shows how long a typical retiree's assets, also known as a nest egg, will last based on the percentage of the assets withdrawn each year. So, A, if a typical retiree has retirement assets of $500,000, how much can he or she withdraw annually if they wish the assets to last 21 years. So, has assets of $500,000. They want it to last 21 years. What do we know? What do we need, right? We know, working with 21 years, oh, that's a terrible line. Let's try that again. 21 years, $500,000. So we want to look at our chart and see where do either of those numbers show up. So the 21 shows up on the chart, right? 21 years, 6%. So that's the percent of assets withdrawn annually. So if they want 21 years, then they're going to have to withdraw 6% annually, right? Well, what does that look like? How do we get 6% of their annual income, or in other words, 6% of 500,000? Well, remember, hopefully, a little bit of understanding of how percents work. Like I said, it's going to sort of come in. I'm going to try to explain it as best I can quickly. But essentially, to find the percent of something, percent of means we multiply. Anytime you see the word of in a problem, it means multiply by that percent. So 6% of 500,000 means we multiply 500,000 by 6%. But we don't multiply 500,000 by 6 because that's not going to make sense, right? If we multiply 500,000 by 6, we're going to get, what would that be? 3 million? So that would imply that they have to save $3 million a year out of the $500,000 they get each year. That wouldn't make any sense, right? They're saving more than they make. So we remember that, oh, right, a percent we convert into its decimal form, 0.06. So 0.06 times 500,000, that's $30,000. So in this case, that means that they would save $30,000 a year out of their 500,000 in order to have 21 years worth of savings in the end. All right. Next question. How much should a retiree have in assets if they wish to withdraw $25,000 annually and wish their assets to last 18 years? So here, we've got the 18 years, so that's directing us towards the chart. But the $25,000 is also going to be important. So in this case, we look at the chart, we find that 18 years they're going to need 7% of their annual income. So in other words, 7% of their assets should be $25,000. So remember I said the of means multiplication. So we can directly translate this statement into a multiplication problem. 7%, which again we're going to make a decimal. So it'll be our 0.07. The multiplication, the of becomes multiplication. Assets. We don't know the assets. We don't know what their assets are. That's the question, is how much assets should there be? So we're going to make that our x value. Or our unknown. And then should be can be our equals. So we get 7% times the number of assets equals $25,000. So this statement, this is the simplified statement, which we simplify even further into an algebra problem. So then we can solve that, right? We can solve for assets by dividing both sides by 0.07. So we get that assets equals $25,000 divided by 0.07, which is approximately $357,142.86. So in other words, they would need $357,000 approximately in order to save enough annually to have 18 years worth of assets for retirement. All right, let's try another one. So this is one that you've definitely run into before, right? Determining a tip. So the cost of Freddie's meal before tax is $28. If a 6.5% sales tax is added to his bill, determine the total cost of the meal including tax. So we're going to do a very similar thing to what I did here, where I'm translating this statement directly into a simpler problem and then taking the simpler problem into an algebra statement. This is how I like to work with percents. I think it's the easiest way to deal with percents is simplify the problem, turn that problem directly into algebra. So we can say, first, sales tax is 6.5% of a meal. That's what this means, right? Sales tax is 6.5% of the meal. And we want to know what is the cost of the meal. So the meal is or what is the cost of the tax on the meal. We know all of this other information. We just need to know the sales tax. So, sales tax, our is becomes an equals sign, our of becomes multiplication. The only other thing we need to do is we need to translate meal into its actual numerical form, which is right here, and 6.5% into a decimal. So remember, 6.5 is 6.5. So the decimal form of 6.5% is actually 0.065. So you have to be very careful there, because that 6.5, we move our decimal over twice to get 0.065 when we translate it into a decimal form. Now, if you didn't remember that, something that you would easily be able to check by your answer being way too big, right? The sales tax on a meal should never be more than the meal itself, which is what you would get if you did 6.5 times $28, right? Or maybe you do 0.65 times 28. That's 65%. That's going to be a lot of tax. And I know taxes sometimes feel like we're paying a lot, but it should still, reasonably, you would probably be able to figure out that the number you got wouldn't make sense. So, now it's just a matter of actually doing that multiplication. We pull out our calculator, we multiply, we're going to get $1.82. That is a sales tax that would make sense on a $28 meal, right? $18.20 wouldn't make much sense. And what would it be? $182 definitely wouldn't make sense, right? So that's how you know. You can check, did I put the decimal in the right place? Does this make sense as a sales tax? All right, so we want to know the total bill now. The total bill is the cost of the meal with the sales tax. So in other words, the total bill equals cost of meal plus sales tax. 28 plus 182 is $29.82. So next, if Freddie wants to leave a 10% tip on the pre-tax cost of the meal, how much should he leave? So tip is 10% of meal, is what that first sort of section says. Tip is 10% of the meal. So, just like we did for the sales tax, we're going to translate directly. Tip is, so is our equal sign. 10% of is our multiplication. Meal. Tip equals 0.10, 10%, times $28, the cost of the meal, which we plug in our calculator and get $2.80. And just a quick note that a simple way to find 10% of any number is to move the decimal point one place to the left. Okay, so if you then wanted to find 20% of the meal, you can just double it. Or if instead we wanted 15%, how would we do that? Well, we would do the same thing. Tip is 15% of meal. Tip equals 0.15 times $28, which is $4.20. But to find 15% easily, we'd find 10% and add half of that amount. So $2.80 plus half of $2.80, which is $1.40, that's $4.20. So that's one way you can calculate tip in your head. If you wanted 20% of the meal, you find the 10% and double it. That's 20%. So there's a neat little trick if you haven't, if you ever have trouble figuring out tips. Okay, our, I believe, last example here, hopefully, is a brine solution. So, some recipes for smoking a turkey recommend pre-soaking the turkey in a brine solution. To make enough brine solution to smoke a 12-pound turkey, we use 16 tablespoons of salt in 2 gallons of water. So if you wish to make 3.5 gallons of brine solution, how much salt is needed? Okay. So what we're going to do here is we're going to do what is called a proportion. So we'll set up a proportion to determine how much salt is needed to mix with 3.5 gallons of water. To set up a proportion, we create ratios where we use information that we know and versus information that we need. Okay, what do we know, what do we need, right? So we're looking at 3.5 gallons of brine solution is our goal, and we want to know how much salt. So we've got, in the original, I've sort of highlighted this information already, but in the original, 16 tablespoons of salt versus 2 gallons of water. So how do we get from 2 gallons to 3.5 gallons? Essentially, we say 16 tablespoons over 2 gallons is our given ratio, and then our unknown ratio is some unknown number of tablespoons per 3.5 gallons. We set these two equal to each other. And instead of putting a question mark, I'll just replace that question mark with an X, because we don't know what it is, but we can solve for it. So hopefully you remember how to solve when you have one fraction sort of equal to another, ratio equal to a ratio, that's called a proportion. We cross multiply. So when we cross multiply, we get 2x equal to 16 times 3.5, or in other words, 56 equals 2x, which we just then have to divide by 2 to get x equals 28. And that's it. So 28, remember to look at your units, 28 tablespoons of salt are needed. Now if we wish to make enough brine solution to soak a 20-pound turkey, how much salt is needed to make it? So in the original, we had a 12-pound turkey, and we used 16 tablespoons of salt and 2 gallons of water. We used all of that information, right? But here, we're looking at how much salt. We don't care about the water, just how much salt will be needed for a 20-pound turkey. So 16 tablespoons of salt versus 12 pounds, that's the given information. So then question mark tablespoons of salt per 20 pounds. Notice that the pounds line up, the tablespoons line up, just like the gallons and the tablespoons did before. We line up our units. That's how you know you have like the right ordering on your ratio, because it's the most common problem in questions like this is just to accidentally flip over one of your fractions. But if you are using units to label each part of your fraction, you won't have that problem. Just know that the units need to line up. So now, once again, we'll replace our question mark with an X, and then we'll do our cross multiplication. So 16 times 20 equals 12 times X, which is 320 is 12X. We just need to divide by 12 to solve for X to get approximately 26.67. And then we don't just leave our answers 26.67, we give our final answer as with its units, with its context, so 26.67 tablespoons of salt are needed. And so that's it for just a few examples of problem solving, but it's certainly not it for problem solving. We're going to be solving a lot of different types of problems throughout this course. So we won't necessarily be working with percents a lot, or proportions will actually come back when we get to geometry, but in general, the idea is for you to take away the ways in which we solve these problems, the methods. When you're met with a word problem, what do? You want to highlight important information. I often color code it in my slideshows, but for you, you'd want to do some underlining, some circling, pull out some of the information, rewrite it so that you've highlighted where are the numbers, what the numbers correspond to, and have you used all of the information that was given to you. Yes, sometimes problems give you more information than you need, but in general, everything is going to get used somewhere. And so if you're not using everything, then you might want to check your methods. Then you always want to check your actual final answer. Check your work. Think about, is it a reasonable answer? But also see if you can plug it back in. Make sure it actually works within the algebra, because don't just trust your ability to multiply or subtract or add. Little mistakes are, everybody makes them. I make them all the time. You don't have to be perfect here, right? As long as you're checking your answers.